Good morning, dear students. I am Dr. Gauri, Assistant Professor from Arts, Science and Commerce College, Ramanandanagar, Pulli. Students, in today's lecture, we will discuss about the chapter Viscosity from paper number 6 of BSc second year, Views on Optics. Students, in last lecture, we have discussed about the viscosity, what are the characteristics of ideal fluid, and we derived the formula for the Newton's laws of viscosity. Students, as we know that viscosity is the characteristic of the flowing liquid in which opposes the relative motion between the adjacent layer of the fluid. So as we compare the viscosity of fluid and honey, then what we got? The honey having highest viscosity as compared to the water. Means water has a low viscosity. So viscosity means the water, kerosene which flows easily, means they having low viscosity, but honey, castor oil can't flow easily because they having high viscosity. So for constant speed of flow we have to apply pressure difference. So what is, I repeat again, for constant speed of flow we have to apply pressure difference. Means we know that there is a force opposing speed of flow. Yes, there is some force which opposing the speed of flow, and this is due to the viscosity. So I will repeat again, viscosity is the property of a fluid by virtue of which opposes the relative motion between the adjacent layer of the fluid. So this is called as a viscosity. Then we have derived the formula for the Newton's law of viscosity. Means there are some fluids which obey the Newton's law of viscosity, which are called as the Newtonian fluids. Means the fluids which obey the Newton's law of viscosity are called as the Newtonian fluids, and the Newton's law of viscosity which is given by this formula. Which formula? Tau is equal to minus mu into dV by du, where tau is the shear stress and mu is the viscosity of liquid. And we also know that dV by dy is the shear rate to the shear strain, and which is nothing but the velocity gradient. Velocity gradient means the decrease in the velocity. Yes, na? As we know that in the fluid there are the numbers of the parallel. What? There are the numbers of the parallel lines, and as we compared from the upper layer to the lower layer, the velocity is going on decreasing. Means for upper layer the velocity is higher, but when we comes to the lower layer the velocity is going on decreasing. Means here I will draw velocity is going on decreasing, and this is called as the velocity gradient, decreasing the velocity. Then now in today's lecture we will discuss about the Poisseless equation. So dear students, Poisseless equation defines the relation between pressure, volume flow and the resistance. So Poisseless equation is a very important equation which used to define relation between pressure, volume and the resistance. And it helps to answer question that how much fluid moves through the vessel. Means how much of fluid which is moves through the vessel, which is given by this Poisseless equation, and which is given by here Q is equal to P by R, where Q is the volume flow, P is the pressure and R is the resistance. So dear students, now here we will derive the Poissulle formula, means the rate of flow of liquid through the horizontal tube. So here this is the diagram which I have drawn already, and I will first I will adjust and then I will explain in detail. Means dear students, this is the this is the liquid. Okay, consider a liquid and which is flowing slowly. and steadily through this horizontal capillary tube. This is the liquid. This is the inside inlet of this capillary tube, and this is the outlet. Okay, here what happens? The liquid which is flowing steadily and horizontally through this capillary tube. Okay, and this capillary tube having the length L. How much length this capillary tube have? This capillary tube having length L. Okay, and having the radius A. This is the radius A. Okay, so students, what happens? The cross section of the capillary tube be the uniform and the difference of pressure between its ends be constant. So imagine a concentric cylindrical layer or shell of the liquid of radius x flowing through the capillary tube. Here what happens? What I told you before, that imagine a concentric cylindrical layer or shell of the liquid of radius x which is flowing through the capillary tube. So the velocity of flow at all the points on the cylindrical shell will be same. Means at all these points the velocity of flow at all these points which is the same. So this will be V. How much of velocity is there? The velocity of all the points of this capillary tube is the V, and velocity of the liquid layer in contact with the wall of the capillary is 0. Means the liquid which is in contact with the wall of the capillary which having velocity how much? 0. So what happens? When it goes on increasing towards axis O dash, then what happens? Here there is the viscous force which is acting on the imaginary cylindrical layer we have derived in last lecture. F is equal to minus eta into A into dV by dx. Okay, so where here A is equal to how much? Here A is equal to 2 pi x. 2 pi x is the area of cylindrical layer of radius x and length L. Means here this area of this cylindrical layer which having radius x, that is the radius x, and having length L. So here A is equal to 2 pi x. Okay, so which is equal to the area of cylindrical layer of radius x and length L. So here we will write minus eta into 2 pi xl into dV by dx. So here, as we know that here the difference of pressure means the pressure at here input which is P plus P0 and the pressure at output P0. At output pressure P0 and it input this is the P plus P0. So what is the difference of the pressure? Difference of pressure is equal to, at the two ends, difference of pressure is equal to how much? P plus P0 minus P0 which is equal to P. So then force due to this pressure difference on the liquid cylinder of radius x which is equal to P pi into x square. Therefore we can write here minus eta. We can write here minus eta 2 pi xl into dV by dx, or how much of force is there? There is a force P pi into x square. So from this equation we can write here dV is equal to minus P pi x square into dx upon eta into 2 pi xl. So we can write here minus p upon 2 eta l into x into dx. So we can write here minus p upon 2 eta l into x into dx. So integrating this equation, so here we get dv is equal to minus p upon 2 eta l into x into dx. So by integrating this equation, what we get? By integrating we get v is equal to integration of dv is equal to v. Here constant 2 eta l we put outside and then make integration of x dx. So here we get minus p upon 2 eta l into integration of x square by 2 plus proportionality constant c1. So we will get this equation. So here we can write finally minus px square upon 2 by 2 4 eta l plus proportionality constant c1. So here c1 is equal to constant of integration. Okay, c1 is constant of integration. So to evaluate the constant of c1, use the fact that the layer of liquid in contact with the wall of capillary is stationary. Means here, as we know that the liquid which is in the contact with the wall of liquid which having the velocity 0 because capillary is stationary, and here x is equal to a, where x is equal to a. So we substitute this in the equation, which in this equation we substitute this equation in this value, means by putting v is equal to 0 and x is equal to a into this equation. So we get finally v is equal to 0. So minus pa square upon 4 eta l plus c1. So we get c1 is equal to pa square upon 4 eta l. So by this we get, by putting this value of c1 into this equation of star, we get how much? We get v is equal to pa square, v is equal to pa square upon 4 eta, how much? 4 eta l minus p x square upon 4 eta l. So we can write here p upon 4 eta l is common, and here a square minus x square. So this is the equation number 1. So this equation number 1 gives the velocity of flow of liquid at a distance x from the axis of capillary tube. So it is the equation of parabola. So here this equation, which is the equation of parabola. This is a equation of parabola. Okay, this is equation of parabola, means which proves that the profile, means the velocity distribution curve of the advancing liquid in the capillary tube is parabola. Here means we shows the here this, that the advancing liquid in the capillary tube is a parabola. So after that, now consider another cork shell of the cylindrical shell of the liquid of radius x plus ds and the cross sectional area between two shell 2 pi dx. Now again consider another coaxial cylinder of shell x plus dx. X plus dx means here in this figure, here x plus dx means here that much of distance. X, this is the x and dash. So another cylinder with how much radius x plus dx, and the cross sectional area between two shell is a 2 pi ax dx. So another cylinder we will consider another cylinder, another cylindrical shell with radius x plus dx and cross-sectional area. How much cross-sectional area? Which is equal to 2 pi x into dx. So, if the v is the velocity of the liquid between two shells, the volume of the liquid flowing per second through this cross-sectional area, which is given by dv is equal to 2 pi x into dx into v. So, if the volume v of the liquid flowing per second, then the capillary tube will be obtained by integrating this equation. Okay. Now we will integrate these two equations because we want to know the volume of the liquid flowing per second through the capillary tube. So we will integrate this equation between limits x is equal to 0 and x is equal to a. So we will integrate this equation between these limits x is equal to 0 and x is equal to a. So we will get v is equal to 0 to a 2 pi x into dx v. So we will get 0 to a 2 pi x into, we know the value of v, p upon 4 eta l into a square minus x square into dx. So what is p upon 4 eta l, a square minus x square into dx. This is the value of v. So we get here, we put constant value p pi upon 2 eta l into a into 0, limit 0 to a. Here we get x a square minus x cube into dx. Here p pi upon 2 to the 4, 2 eta l is a common here, and we here x a square minus x cube into dx. So here we get pi p upon 2 eta l into a raised to 4. Okay, a raised to 4 upon 2, because here integration of x is x square by 2, and we here put instead of x a, we get a raised to 2 minus integration of x cube is x raised to 4, we put value a here, then we get a raised to 4 upon 4. Then finally we get pi p a raised to 4 upon 8 eta l. So therefore we can write v is equal to pi p a raised to 4 upon 8 eta l. So the coefficient of viscosity of the liquid eta is equal to pi p a raised to 4 upon 8 lv. So this is the standard equation, or this equation which is called as the Poisseless equation for the coefficient of viscosity. So when we know, if we know the value of P, A, V and L, the coefficient of viscosity of the liquid can be easily determined. Means by knowing all these value P, A, V and L, we can determine the value of eta. So dear student, this is the expression for the what? This is the expression for the Poisseless equation, and which is very important equation, and which by using this relation is a gold only when the flow of the liquid is a streamline and the pressure is constant over easy every cross section.